We started.
تقبل. So, hello everyone to the third session of AI Summit. In this session, we will host AIT SAID Azzedine, PhD at Telecom Paris and BNP Paribas. In this talk, we will talk about failures and trustworthiness in LLM-based multi-agent systems. So, the word is yours.
Hello, everyone. Thanks again for the invitation. Thank you, School of AI. In this talk today, I will try to really cover with you horizontally the domain of multi-agent systems, what they are, how people are excited about them, how do they fail, because they have a lot of failures, how to make them trustworthy, and why this is becoming a little bit difficult with time. Just a bit about myself. As Amin said, I'm doing a PhD now in trustworthiness of LLM-based multi-agent systems. This trustworthiness is special. We will see at the end how it is related with time and game theory. I had the honor of being also a technical manager at School of AI before. I had the pleasure of hosting a lot of workshops / presentations that you will find them in this in this GitHub repo. About my recent work, I did 2 interventions at ICSE in Rio, of course online. I talked about COBOL retro documentation, COBOL, the language, the programming language used in bank. We tried to document it using LLMs, and the other intervention is related to reinforcement learning, where we use it for root cause analysis. I have also an accepted paper at this amazing conference called Autonomous Agents and Multi-Agent System that is more related to the topic of today. And of course, I will talk about it in the next days if you are following me on LinkedIn. So our journey in this talk will start with somehow a revolutionary invention of our era, an entity that will have a text as input and that will provide for you a needed text as an output. This is a very nice summary of LLMs. And of course, the generation of the output is made token by token. I won't explain LLMs in this talk. We won't have time. And you should know already that this setup feels like somehow a prehistoric setup. It's almost no one is using LLMs seriously like this now. Even your favorite provider, for example, OpenAI or Claude, is using a more advanced setting. This advanced setting is needed because there are some questions that LLMs alone cannot answer. For example, if you ask it about something that is inside an environment, for example, a PDF file, or we can use an LLM in a conversation, and if the conversation goes really long, they cannot get what we said 7 messages or 8 messages before. Of course, this is a prehistoric setting. Now they can really easily catch a whole conversation. And also, they have a knowledge cutoff, so they don't have updated information about what's happening in the world. So if you ask them something after their knowledge cutoff, they might not answer. So this advanced setting is the one that I'm showing here. We can solve the previous questions and problems we asked, and using some entities we call tools. So those tools are just deterministic code that the LLM will trigger at a certain point of the execution. The tools can do many things. For example, they can search a database, they can execute commands, sorry, and also more than the tools, we can use a memory where we store uh, important information or the whole conversation. Some agents use, not all of them, use a special verification step where if we are not having the result we want, we go back and reloop until we get it. You need to know that this vision of an agent is very specific. In fact, it is a perspective or a specialized definition. There is a lot of definitions, other definitions of agents, and in fact, you will feel it through all my talk that the field, the domain is really really large, and everyone is seeing it in their specific perspective. And I'm trying in this fog to have some wisdom in the middle, some consensus we created together that I will present, of course, at the end. So the tool using perspective of LLMs has been introduced by Meta in 2023 with this NeurIPS paper. They this perspective has inspired many other frameworks and methods, and it became the most, used, for example, in LangGraph. And the tool, the LLM, is the one choosing the parameters of the tool. But other frameworks can also try to make the LLM create the tool, or even use the tools and the parameters that are already predefined, and the LLM will just decide to trigger the tool without giving parameters. You need to know also that there is, of course, another famous perspective from Google research this time. It's the one that is reflective. And I think when I talk about agents, most of you will see this perspective directly. Here we are more in sort of loop. I think I will explain it here more better because there is the diagram. So here we of course we are just manipulating text because it's an LLM, but in somehow a special way. There are still tools. You can also see that there is no obligation of using a memory or a state, just like the other perspective. But of course, we need to save the actions in order to have the trace. But you can feel here that it's more about the loop, the thinking, and the tools. It's just another definition that quite do the same thing at the end. So here we just have one thought, which is a generation from the LLM. Then the LLM do an action. What's an action is just triggering a tool with a parameter. For example, it chooses here Apple Remote. This is taken from the image is taken directly from the paper. Then after the tool will answer and we will mark an observation. This observation will lead to another thought from the LLM where each step we do an evaluation. Why? Because at some point we need to finish, and this finishing line, this is very important, is triggered by the LLM itself. So the LLM will say, okay, I have reached the end. So the action will be generated by the LLM called finish. This is very important to see because we can loop infinitely. Of course, there is some, how do we call it? Some configurations we add, some code we add that we stop the execution if the loops are getting too much loops are getting executed. So as I said, an agent is defined very largely, differently in this domain, and we can see that not only researchers are proposing definitions, but also the industry, such as, for example, Anthropic. They see an agent as an entity that directs its own process. This is very different from the old definition, when we clearly see that the system that we as developers of the system tell the LLM what to do, and not giving it that autonomy. to accomplish the task. This is a little bit different from the definition of OpenAI. You can see that those two does not necessarily go in the same direction. This one from Hugging Face Small Agent Framework I related after to discuss. We can also have a remarkable mention for a very strong domain that I will mention also throughout this talk, which is the actual classical domain of multi-agent systems. Because when we talk about an agent or a multi-agent system, now we directly refer to an LLM. But this is not the case actually, because there are 30 years of theory and knowledge and books about this domain, about agents themselves. And agent can be actually anything, a robot or any entity that is autonomous and social. We will see the definition here. I am referring to Michael Woodridge, that is a pioneer in the field. He wrote a book. We will see it afterwards. So we can see that there is a lot of debate in this domain. And the consensus that I try to use in this talk, so we don't diverge a lot, is that an agent is an LLM-based agent, of course, because an agent is is something else from the classical theory. An LLM agent is an entity that use an LLM in order to decide actions and execute them. An action is, of course, a triggering of a tool. And here, an important thing is that the goal can be implicit or explicit. What is an implicit? The explicit goal is something we all know, but the implicit one here is some goal can emerge in the way of the orchestrator or the planner that was not already defined by the developer. So the LLM have the can have this liberty, or can have this reactiveness to define a goal and follow it that is implicit, that I didn't know before. For example, we can have this very famous multi-agent system to study, to see how the authors have used those concepts, that these consensus, to code their multi-agent system. This is a very famous multi-agent system. It has this amount of stars on GitHub, and some people are using it in order to make real trading decisions. Of course, don't do that. Read always what the LLM is saying. But the good thing is that they used tools, and those are just grabbers. They contact APIs to grab information in real time from Twitter, from Reddit, from many sources, and they give it to a team of 2 agents. Those will analyze in a bullish way or a bearish way. I mean, an optimistic or pessimistic about the information. Of course, they discuss the information related to, for example, a trade. So they give it to a trader that have, of course, a specific task. Those, you can see each component having a prompt template. So the bullish team will have, you are, for example, the bullish team of trading agent, you need to do that and that. So it's just prompting at the end of the day. It's just text that we are trying to force and give to the LLM, and also information that are in real time, of course. And at the end, a manager that will read all the conversations, the discussion of the research team, the decision from the trader, and some other useful information to make a decision. The decision at the end will be either buy the assets, or sell them, or hold, don't do anything. This is a very good example, a famous one, because why did I choose this example? Because it is accepted by the community, because everyone is studying it and starring the repository, and this is not the case of so many other architectures. I can come with a lot of designs for the same problem, and I can find different results. Some design from the multi-agent system that I made can achieve the task, others no, others can achieve it better. So there is no actual plan in order to create or design a good multi-agent system. It's somehow just trying and improving, and that's it. So from this example, we can have from those two surveys also a sort of definition of multi-agent system. They are just LLM-based agents as we defined them before in the consensus. And the key word here is interaction. So the behavior of each component from the beginning to the end to end, is really being changed and being updated by other components. So that's it. This is the key thing to remember, because when something will fail, we will see how the whole system will be also touched. Other examples, the state of the art also propose different angles on how we can see multi-agent system. They can be centralized using an orchestrator. They can use a shared memory. We can also give a memory to each agent alone without giving others information about what is the current agent is doing. We can have parallel execution. For example, those two types, they work in parallel, but the first one are more layered into a workflow, but the decentralized is more in an exchange and debate, and we don't have this sequential execution as the layered one. You can find a lot of frameworks that do this and present how to code agents like this. Other papers, for example, MetaGPT, which is an ICLR 2024, is very famous. They propose a multi-agent system that they code. They do not provide a framework. They do not provide something on how to code multi-agent. They provide a multi-agent system in order to code. So they basically, their inspiration is how a human team will code something on GitHub, and they directly mimic this into a multi-agent system, and they provided it. So you can find those type of papers. This is very similar to trading agent, in fact. This is what they provide. As I said, other can tell you, okay, this is my framework to do multi-agent systems. They provide, as we call, abstractions or classes that you directly use. You can even use them directly, visually, or in a graph like Crew AI. It's a no-code. It has a no-code, how do we call it, feature, but specifically, you can directly use those classes, inherit them, and code directly your multi-agent systems. This is, for example, Autogen. So this is an interesting thing because they see a multi-agent systems differently, not like small agents see them. Microsoft, Autogen is from Microsoft, and everything is an agent, of course, but there are some types. The conversable agent is an agent that will use tools, that will communicate with the user, that will provide text. The assistant agent will only provide text, nothing else. It's somehow used at the end, at the very end of the execution. The group chat manager is somehow an orchestrator that will tell everyone what to do to plan. The user proxy agent will provide code, talk to the human and ask him questions, follow up, and or verifications. Instead, small agents, they see all the agents as one class, which is, of course, this one class can be also specific, and also this needs to be mentioned. In Autogen, we can also create a specific or custom agents. You don't need to use their abstraction, but they propose, and they say, okay, this is how we see multi-agent systems. So I was saying that small agents see everything as a coding agent. So the agent will express his actions. Sorry, its actions is not a real person, the agent. So the agent will express its actions using Python code. So it will produce code. Maybe an intuition to code good small agents architectures is to use, for example, a good coding agent. I don't know. But yeah, so from the beginning until now, we have seen that it is very hard to agree in this domain. But something that we all know in this domain, of course, that there is an opportunity. Of course, we can code agents in many ways as we want. We can propose frameworks. We can propose methods that maybe don't work someday or on a specific task. But we know that this multi-agency is similar to how multiple humans will work together. So there is an advantage, even if it is intuitive. We don't prove this. And for the matter, I have a paper that proves the opposite, that a single LLM can outperform a multi-agent system. But we feel intuitively that there is this opportunity, and it is. The paper existing that we will discuss after does not guarantee that always this is always the matter. So yeah, of course, an LLM, a single LLM agent cannot solve a complex task, a long horizon task, because of the context window. So if you want to really see something in depth, the context window, even if it is that big, the LLM can hallucinate on some parts. So you need to delegate expertise and isolate this expertise. Of course, this opportunity comes with major problems that we often see on LinkedIn or Twitter or on the news. An agent has deleted the whole database of a company. The agent have made the global mistakes and we don't know what's happening, and blah, blah, blah. So multi-agent systems, they fail for sure. But why do they fail? Because there is a big surface of failure. So adding more components, you add more failure to this surface. The first one could generate a wrong output. For example, we can fail to retrieve the needed data from local database or from the internet. The orchestrator, for example, can tell the others to do a wrong decision, etc. And the dangerous thing is that even if everything is working well, if one thing is wrong, the output, the final one, can be also wrong. For example, we assume LLM agent 2 is dependent on the output of LLM agent 1. So this is the dangerous part. And we said it before, the crucial keyword in all this domain is interaction. So failure is inherited by interaction. If there is an interaction and a failure, there will be, for sure, the system is wrong at all. So studying failure is important in order to improve multi-agent system, in order to avoid them to delete the whole database of a company. That's why you can find a lot of papers talking about multi-agent system failures, like this one published in NeurIPS. They propose also a data set. So their study, they just collected a lot of multi-agent systems, tested them on many benchmarks using different LLMs and using three methods of annotation. They had the traces and they annotated the failures on them, leading to this number of traces and this important statistic that, in fact, almost all the time, those multi-agent systems fail. For example, a type of failure is we have an agent one that is a foreign agent. It knows the API, expects a phone number, and tells the other agents this is an invalid credential. So the other grabbing agent or retrieving agent tries to use the same login once again. This is a failure because the agent failed to share the right information, not because there is not something that is done. And in the same paper, they classified the failures in a very interesting way through three categories. And we will see in other papers they also share those types of big global categories. In the first one, we can see that the failures, there is an unclear task, unclear roles, uselessly repeated steps. We have lost maybe the objective of the conversation, or we are finished, or we don't have enough conditions to finish, or anything related to termination conditions. Those are more related to the developer. That's why they classified it as a system design. This one is more about communication of the agent. So anything about asking for clarification failure, we have an information and we withhold it, we derail from the task, we ignore another agent information, or we forgot, for example, because of hallucination, the reasoning and the global goal of this task. And finally, this is also very intuitive. The final part, are we done? The checking at the end, is this task finished? Are we done really or not? So anything, whether the answer is complete, correct, or final. Other papers are interested in that matter, but for example, this one, but only in the agent failures, not in a multi-agent scope. We can find a good amount of similarities, and almost the same type of failures, but in an agent scope. The second one, of course, is really similar to the first one, and even we can see here the three failures distinctions, except that at the end, the first paper dedicated a whole section about termination and verification stage, which is not here the case. They introduce it inside. Yep. So we have missed, in fact, something really important. When we talk about failures, we think erroneously that the failure will annotate itself. This is wrong, because we know the failure, we know that the multi-agent system is not getting the answer quite right or correct, or is not accomplishing the task. But where is the failure happening? This is hard to get. This is very hard to get, and this is why this is the objective of the two papers we presented. As I have written here, the failure is easy to observe because we are using the system, but hard to attribute. Where is the failure? Which agent caused the failure? At what level? And when? So in those two papers, we can see that we start always by human annotation, because we trust humans, we trust the experts, but we don't want to annotate everything. So we annotate just a sufficient amount of traces, like here 150 and 127, sorry. And then we come with a method to continue on this. They usually use LLM as a judge, but they are grounded with the truth. They are grounded with an already really high quality data from humans. As for the first paper we presented, why do LLM fails? They provide this dataset called MAST. Some other papers also use LLM as a judge directly, but of course we don't want to do this, because without grounding it, of course, we need the LLM to see and touch something that is correct and not hallucinate half of the answers. Another hard thing to do, aside from annotation in this multi-agent scope, is to perform a comparison, to perform an evaluation, in fact. There is this paper that is very interesting. It doesn't have much citations yet because it is very recent. They prove why single agent LLMs can outperform multi-agent systems in some use cases. But the good thing they did is that they used a fair comparison, because before we were comparing the two settings in somehow an unfair way. Because in the single agent system, we just provided with one call, one reasoning trace, and the multi-agent system, besides it, we give it an unlimited reasoning budget. So what they did, they just fixed the budget in the two use cases. And the amazing result is that in those conditions, a single LLM can outperform a multi-agent system. Of course, they used only two data sets, frames and this one, and those families of LLMs. Of course, this is not generalizable. It just my way to say that this domain needs some wisdom, needs to take time to read about it, needs really some how do we call, yeah, just slow down before you enter in this domain, because there is a lot of buzzwords, there's a lot of marketing happening in it, and yeah, try to read and see the insights before. I will continue on those advices at the end. I dedicated a whole slide on it. So why are we talking about trustworthiness in the first place? It was a keyword in the talk, and we did not mention it until now. The key paper for trustworthiness for multi-agent systems and how do they behave is from this team at Oxford, and from also Michael Woodridge himself, who is a pioneer in the multi-agent system, the classical domain, the old theory, as I said in the beginning of this talk. So he was a supervisor of this work. And in this paper, they claim that in order to have more trustworthy, more reliable, more aligned multi-agent systems, we need to address three problems. The problems are, first things, large language models do not have social behavior, and the environments that are built now in multi-agent systems, they are a little bit LLM-centric. They are not true environments. We will see the condition of an environment for a multi-agent system. And the final thing is that how do we coordinate and make those LLMs cooperate between them has a lot of issues. We can start with the first social one. So, of course, I cited a book, but also there is this one that is an interesting also mention. So both of them, they agreed that a multi-agent system is itself an entity, of course, that is also formed of a lot of entities, but we can see that there is a very large and diverse components. It can be a human, we can have a tool here, we can have a database, an external system, anything, and we have agents here. It can be an LLM, it can be a machine learning model, it can be really also anything. It needs to be social, it needs to cooperate, coordinate, to compete with each other, it needs to negotiate, to send information, to update an environment, and it needs to be reactive. So alone, autonomously, get an information, understand something, and propose an action about this observation. It needs also to be proactive, reactive and proactive and social. So this is the vision on social behavior. Of course, this is not what we see in current large language models. They are not really like that. And a lot of people have studied theory of mind of large language model. And by theory of mind, it's just the ability of how do you call it? Is the ability of an entity to understand the beliefs, the thoughts, the desires, and emotions of other entities. For instance, people, we do this in an innate. It's an innate ability in humans. So, large language models, of course, have a sort of theory of mind ability in them, but when you read all those papers, you can tell that this is more of a literal theory of mind. So the model can answer a question about what another agent or a human know or believe, but they don't have a functional theory of mind. So the agent cannot adapt on its own its strategy or its planning dynamically in a response to another behavior. It can be anything. I mean, an agent behavior, a human behavior, or a tool behavior. We cannot that easily change a whole strategy using LLMs, of course. And the solution for this from the team from Oxford, they claim that we need to restudy how LLMs are being trained in the first place. We can introduce a loss or something or an evaluation or I don't know, or a fine tuning on top of an LLM to make it follow more of a social goal instead of just being a good assistant. The other thing they try to understand really well is an environment, and they provided a whole bunch of conditions on how can we call this an environment in a multi-agent system. Not everything can be an environment in a multi-agent system, especially the ones that are we using now in LLM-based multi-agent systems that are really LLM centric. We are building the environments on top of the LLMs just in order to have those quick results. So an environment needs needs to be existing outside. It needs to have it needs to be real, not just an agent. Not, it's not it does not need to be really understood or implicit like we are using it in LLMs. Agents need to act on this environment. There will be consequences on this environment from the LLMs. Also, we can have the environments changing on their own without the LLMs or the agent touching this. It needs to be heterogeneous, a lot of components in it, many different things involved in this environment. It can be manipulable. It also need to be partially observable from the agent. We don't need to all the agent know the environment on its whole. They only need to know what they specifically target, the task that they need to observe and work on. They need to know it, and that's all. Because it's not efficient, and each agent know everything. Those two are what we are doing in LLM agents now that are really that do not fit the old multi-agent theory. For the coordination, we can have those two examples also. We can see that in our typical use case now, we often straightforward do this. We orchestrate, we declare a bunch of LLM agents, we make them use, and everything is communicating in a text. And we are happy with it. But a researcher in the domain of native multi-agent system can easily detect that our system lack asynchronicity. So all the agents, in fact, are waiting for the orchestrator to provide something in order to continue their task. Even if we don't use an orchestrator, they are waiting for each other to do something. They are waiting for someone or something in order to do an action, which is not really the case when using robots or using old agents. Of course, the communication is mainly used with text, but before we were using really protocols, for example, CUML and others, where we specifically say what's happening. For example, we declare an action, we say that this message was sent to an agent, to agent A from agent B. There is more details to the communication than ambiguous text. So the authors have ended there. Of course, this image is not taken from the first paper. This is another paper, but the authors have ended their claim. In order to have more trustworthy multi-agent systems, we need to address those three problems. But is this the opinion of other researchers? We can see that trustworthiness of AI in general has been studied thoroughly, and of LLMs also in details. But as I see now, as the state of the art, as I see it now, there is really not that much work on trustworthiness of multi-agent systems itself. That's why we will try in the following slides to follow uh, the same framework or the same ideas that that trustworthiness researchers have done. So how do we know an LLM is trustworthy? It needs to be reliable, giving good information, safe, doesn't harm minors, for example. It needs to be fair with all different types of people, resistant to hijacks and prompt injection and social engineering, explain itself. It has social norm without a lot of toxicity, and robust, for example. One good thing about robustness is that every time I give it the same thing, it will give me the same result. The same input need to lead to the same result. This is not possible, in fact, with LLMs. This is my opinion, because they are non-deterministic entities. So up until now, we have seen that errors in multi-agent systems propagate, so we cannot really trust those systems, and agents can miscommunicate. So we do not trust their shared understanding. This is somehow, this table show where trust is being somehow, how it is residing, where it is residing in a multi-agent system. We need to trust the agents. We need to trust their orchestration. We need to trust the verification steps on it, and we need to we need to trust all the components alone and globally. So this leads to this divergent definition of trustworthiness, because trust in an LLM is not the same as trust in an agent itself, and is also different from trust in a multi-agent system. And how do we solve this problem? How do we the last thing I want to talk about is, what is the solution? In fact, I'm talking from the beginning about problems and failures, and I hurt your minds with all of those things. But where is, in fact, the solution for everything? This is somehow a research direction that Google DeepMind is currently investigating. And also in our lab, we are trying to work on game theory in order to uniformalize all those divergent paths and divergent claims in the state of the art, in order to have one big understanding, one big definition, for example, and something that we can work on. In the next slide, we will see how everything come to a sense when we use game theory. But before, let's just introduce game theory and what it is. So it is the science that studies strategic interaction between decision makers, mostly for humans. It was well known with games from a game called Prisoner Dilemma, when two agents can cooperate or defect, and we study their behavior and their strategy to maximize each other outcome and also the global outcome. And in game theory, trust is something really inscribed inside of it, because agents, as they cooperate or defect, they trust each other. And for example, trustworthiness will directly come to a definition if we define trust. If you are the one that is trusting the other, so if you are the trustee, then you have trustworthiness, because you are worthy of trust. That's all. And trusting someone is just giving the possibility to the other to harm us, to defect in game theory, for example, to lead to an outcome that is not good for us. And our objective using game theory is to create something that is trustworthy, but of course in time, because we can have an agent be, it is an LLM or a human, for example. It can be a human. We can be trusted. It can be trustworthy for a limited time. Today they are cooperating and everything is amazing. But what if one day this will stop? And the non-deterministic capabilities of LLMs does make this risk really really happening, really real, because Claude, as we saw in the previous news, it is being tested every day by Anthropic, but when we use it in some environments, it become non cooperative or defecting or dangerous in some places, in some use cases. So yeah, this one. Yeah. So in order to have sense of everything, this will be there's no much content I will share after this. Just some summaries. In order to summarize everything, using game theory lens, we can see agents as players. We can see their actions as the strategies they follow. We can see the goals they are trying to solve inherently. I mean, the task that is being done by them actually as payoffs and rewards. We can try to make coordination methods that are well known in game theory in order to make them cooperate, and etc. So with game theory, we can have a consensus. We can understand what each component is, how to modelize them, and like this, we won't have many divergence. We sort of agree with everything. That's it. So as a sort of summary of all what we did in this presentation, so you can see this slide as, if I want to summarize 3 insights from this presentation to you, those are the 4 insights. So when we add agents when we always add agent to a system, it does not actually improve the performance under the compute budget. You need to study this, you need to research this before doing anything. If you add, maybe it will be good, but not always, as we saw in the first paper. Secondly, how do errors inside my multi-agent system, how do they propagate? Is my architecture, because you can have a multi-agent system that cannot easily propagate errors and failures. We don't know how, but you can find out a good coordination protocol to make this failure stay. But right now, we believe that all the coordination protocols used can lead to failures. We cannot modularize, and you cannot send failures only if you cannot send failures only if you are using one agent. So, but we believe maybe we can have something. We are optimistic about this one. Third thing, can we design protocols that are truthful, that can be calibrated to cooperate, to make the agent cooperate with each other in a very stable strategy? Are the agents, are the LLM agents always be truthful about their results? Will they make a dangerous action someday? This is interesting also to see and to understand. Those are sort of questions, but in the same time, insights for you from all what we have seen. And last thing, how do we evaluate trustworthiness? Is it a system level feature? Does the LLM having a good trustworthiness? How do we say? Trustworthiness percentage means the system is good. Not always. You need to study everything in your system and see every single component on it in order to have a claim and to present that this is a good system that I built. That's it. Um, for yeah, I was talking about advices earlier in this advice earlier in this talk, and I have actually one advice for anyone that will be working or want to work in mediation system or just is interested. I think you do not need to learn a framework. Don't try to use LangGraph or Crew AI or small agents. Don't code. Try to understand. Try to read what is a multi-agent system. How does it coordinate itself? What are the messages sent? Try to study it thoroughly. Why not maybe make a solution in paper using a paper and a pen, a theoretical solution, try to see it really thoroughly. Then afterwards, try to learn how to code. You can easily code multi-agent systems without using any framework. You can use Python, plain Python to code multi-agent systems easily. So that's it. Always also before ask those three questions before claiming that I have a solution, because this is important because there is no such plan or way to tell that this is a good solution. The community need to give its feedback, and experts need to give their feedback to your solution in order to say that it is a good one. But yeah, that's it. It is an iceberg, in fact. The domain is an iceberg. Thank you for your attention. Follow me using this QR code, and happy to receive all your questions and remarks and anything you want to discuss.
Thank you, Azzedine, about all these informations. Sincerely, that was the first time someone talks about agents in research for me personally. It was so exciting. For the questions, Anis is talking about can we improve multi-agent systems with such techniques like fine-tuning? Like anyone talks about using best orchestration and all, but what about fine-tuning and maybe error reinforcement learning to improve multi-agent systems? What do you think?
Of course, those like reinforcement learning with human feedback has been used to improve theory of mind of LLMs. It is a good way, it is a correct way, but it is somehow a costful solution. You need to gather the data, you need to, yeah, this solution has a cost. But I would ask a question for Anis, telling him, what do you mean by making them better? Making them more accurate, making them more trustworthy. I mean, if you ask trustworthy, then you did not listen to the talk, because the conclusion is it is hard and there is three ways to do so. But if you mean accuracy and using them, I don't think fine tuning is the first solution to use because it is costful. I think maybe looping in a trial and error, changing every time the architecture to see if you can tweak something that will make it better, if you can add a component to make it better. Yeah, if you maybe add a tool that will improve the context, the information of the LLM, of the agent, to make good results.
Thank you. That was very clear. Very clear. I want to ask, what was the intuition that pushes scientists and engineers to deepen in the multi-agent systems? I mean, what about using one agent, but influence it to use it in the best way the tools and the environment, interact with the environment?
In fact, I presented a paper that instead of jumping into a multi-agent setting, we can use just one LLM and solve a task really, really good. The intuition behind this is that having a whole LLM holding all the context for a very complex task is not efficient. because we know that LLMs dealing with a very long context can hallucinate. They can forget a lot of details. They can, I don't know, uh, it is better intuitively as we human operate to isolate an expertise and try to benefit from this expertise between a lot of entities. Someone would code something, another will search about another thing, and then all the paths meet in an orchestrator, for example. This is the intuition, but it is a good question because it is an intuition. We don't know why they work, and there are papers that claim that they are not a good solution for every use case. We can solve a lot of problems using just one single LLM.
Thank you. For the next question, I want to ask. This is my question. I want to ask if there is such a research that were about like can an agent correct and discover that another agent was wrong in its response? I mean, you said that an agent that made the wrong response can affect the whole orchestration, but can we really? I don't know, but can we really make an agent discover the errors and the wrong answers of all the agents? What do you think?
I mean, you can use it is a question related to evaluation of the output. So there are a lot of papers that claim that in fact an agent, an LLM, is not a very efficient solution to evaluate the outputs of another LLM. There is a problem, especially if it is itself or it is the user. There is a problem that LLMs suffer from some uh, bias to itself and bias to they easily agree with the solution without criticizing it enough. Some
Yeah.
other agents, because of the scaling, can have this ability to criticize and criticize pertinently. But of course, this is not a behavior. This is not an ability. It is tightly related to the training data. If the training data has this an abundant amount of uh, criticizing things, the LLM could criticize easily. But globally, using an LLM as a judge is not a very good way. We need formal methods, we need deterministic evaluators to robustly, to reliably say that this output is not good. Giving it into an agent is not a trustworthy solution, to
Mhm.
talk in my terms.
The next question is by Malik. He asks, uh, apart of from LLM shift, so from smart learning and all of that, he says, could we improve accuracy in the agents in a systemized way? What do you think?
Improving, I mean, improving the agent itself, we can do it through fine tuning, through better prompting techniques, as we also are discovering right now. Um, there is a domain called context engineering that is really interested in how can we provide the most efficient, the most optimal context for an agent to perform his tasks. It's somehow an advanced form of prompt engineering, and this is can be done to improve the agent. But in order to improve the system, it becomes strictly harder than improving one agent. We don't know, in fact. I cannot provide a very confident answer to this. I could give you intuitions, but yeah, we don't know yet. Dit autrement, we would need to learn some return function. What do you mean?
Mhm.
That was in reference to the question of verifying output. Ah, okay, yeah, we can also this is a good one because we can from text have a return, calculate a return, calculate a reward in order to exactly calculate a score in order to train or fine tune the LLM in a reinforcement learning uh, setting to make it more social or more better in general.
Uh, I want to ask you, you have, attends, yes, asking.
Which is the whole concept exactly, which is the whole purpose of reinforcement learning with human feedback.
I want to ask you, you have talked about the research side, but about the engineering and the production side, I want to know if it's, I mean, is there some techniques to avoid all the problems that you have talked about in the production environment? I mean, when you host your multi-agent system.
In I mean, the most advanced ways of using multi-agent system now is using them through model context protocols, servers, defining the tools, having all the agents read the tool list, try to create indexes. There is a lot of good things in LLM ops, LLM operations that are really interesting to read, but of course they're still not as wise. I mean, you can read any, you can see security breaches in MCP protocol. You will fear using MCP in a production setting. There are also agent to agent protocols. It's famously introduced from IBM, I think 1 year ago. And I think it's interesting to read about how they are trying to orchestrate communication between agents using a framework. But of course, you need to know that in production, you don't find lane graph agents. You don't find they are more like tests. They are more like used in MVPs, in just trying something if it works. In an industry setting, we do not use something that is that non-deterministic. I mean, we need to trust it before deploying it. That's why some people are coding their agents or their solution directly in plain Python without many frameworks, studying the matter really thoroughly. And that's the purpose of all my PhD, in fact, how to make them deployable in a production matter.
That was great.
Yep.
There's just someone asking about what frameworks are you using in your research and then your engineering site, and to just send some frameworks to start learning multi-agent systems.
Some resources, some frameworks, you said.
Yeah, frameworks.
I would advise to start with LangGraph, but as I said in the talk, I don't advise anyone learning a framework. You need to learn the theory of multi-agent systems. You need to learn the concepts of it. But I mean, small agents on Hugging Face give a good course about how you study those things, but you need to know that they provide their perspective on multi-agent systems. At the end of the day, you can talk with a researcher, with another person that are working in multi-agent system, and maybe you don't understand each other. You will always use coding agents, and for another person, this is not an agent at all. To answer also your question, I try to code my agents in plain Python. I mean, I don't we I it is an opinion. I don't see why I should use an abstraction, uh, because it is already easy. We just call an LLM and try to make it to coordinate it, and that's all. I don't think we need a whole abstraction, a whole framework to do so. Resources, as I told you, you just need, maybe as a researcher, say, to start with surveys, read the papers. But yeah, I think you should see and be interested to Landgraph. Landgraph as a first step, see maybe the paper React, and then follow me to learn about failures of of multi-agent systems. Thanks a
I
lot.
think that's
I think that's all. Yeah. Thank you, everyone. Thank you again, School of AI, for the invitation.
thank you, Asdi. صحيح.
Thank you, Amin. Take care.